Hello everybody, my name is Dr. Kwang. Today I will be talking about deformation of solids. Okay, let's start the lesson. Okay, let me share the screen first. Okay, so I hope you can see the screen I'm sharing. Okay, so deformation of solids. And that's the learning outcome about this lesson. So just quickly scan through this. As you can see, the learning outcomes are differentiated with different color. Now, let's start with an activity. So I will be doing a demonstration. So I'll show you something. And then after the demonstration, I want you to describe the demonstration. Okay, so I will come back to this this page later. I just stop presenting, stop sharing the page because I want to show you, because I want to do the demonstration for you. I got the elastic band. I'm doing the demonstration now. So I got the elastic band and I apply force to make it longer. And I remove the force. Okay. Now I got the blue tack and I'm doing the same. I just stretch it, apply force to make it longer, and I remove the force. So that's the blue tack, and that's the elastic band. Okay, so that's the end of the demonstration. Okay, let me share the screen again. Okay, so now, oops, sorry. I hope you can see the screen I'm sharing. Yeah. Now I want you to describe the size or the shape change of the elastic band and the blue tack when they are pulled. Okay, so you can write your answer in the your worksheet, and feel free to use any of the terms given here. You don't have to use them, but if you want to use them, just feel free to use them. You can pause the video and then spend 1 or 2 minutes to complete the task. Okay, now let's have a look at the answer. So that's basically my description. So about the plastic band. So when the plastic band was pulled by force, it deformed by extending its length, and it went back to its original shape when the force was removed. So the deformation caused by the force is temporary, so it's temperate. And about blue tack, when the blue tack was pulled by the force, it deformed by extending the length. That's the same as the elastic band. However, it kept its deformed shape when the force was removed. So the deformation caused by the force is permanent. Okay, I think it's very easy to tell the difference between these two different types of deformation. Now I just give you the definition. So if the deformation, after removing the force, the deformation just disappeared. I mean, the shape of the object that goes back to the original shape, then the deformation is called elastic one, elastic deformation, just as the case when using the elastic band. And another type of deformation is called plastic one, and just the one I demonstrated using the blue tack, because after removing the force, the deformation is not disappearing, so the deformation is permanent. Okay, so that's the difference between elastic deformation and plastic deformation. I think it's pretty easy to understand. Let's do some further discussion. Now I want you to look at the diagram. You can see a spring hanging on the ceiling, and then if you add a load here, of course, because of the gravity, so the load gonna pull that spring longer. So the weight of the load pull the spring longer. Now I've got a question. Do you think the deformation of the spring elastic or plastic, and why? Okay, give you a few seconds to think about it. Okay, you may pause the video to discuss this question. Okay, now I just give you the answer. So it actually depends whether the load is within or beyond the elastic limit. Here I just highlight that keyword. So that's a new concept. So what does elastic limit mean? Okay, let's just make it bigger. So the elastic limit is the maximum force that can be applied to a wire spring such that the wire spring returns to its original length when a force is removed. Okay, I think it's quite easy to understand. So for example, if the load is not that heavy, then it just slightly stretch that spring, and after removing that load, the spring gonna go back to its original size, and then the deformation of the spring would be elastic one. However, if the weight of the load is too heavy, if it's go beyond that elastic limit, then that spring gonna be overstretched. After removing the load, it won't go back to the original length. That means that deformation would become plastic. Okay, so and then that point, that maximum weight of the load is the elastic limit. Okay, let's have a look at more example. Yeah, so the same is this, the spring stretched by the weight. Let's say that because of the gravity, it applies force onto the spring, and the spring will be extended. And then I think in GCSE physics, we plot the graph showing the relationship between extension and the load. Okay. And so in most of the cases, it's actually not in most of the cases. So if in some cases, it follow a linear relationship. That is, for example, if I say the extension, of course, is just E, and load is F. And then in some cases, it follow a linear relationship that is F equals K times E. And this is known as Hooke's law. Yeah, I hope you still remember. And that equation just tells us that relationship between F and E is linear. F is proportional to E, just as shown here. Yeah, of course, before the P point. So you can see a P point here. So when the load is smaller than P, it perfectly follows that relationship. Okay. However, when the load go beyond that point, you can see the straight line become a little bit curved. That means it doesn't perfectly follow that relationship. So that P point is called proportional limit. So that means within P, the load of extension follows Hooke's law. That is that linear relationship. Okay, I think this is GCSE stuff. Now, so we just discussed about E point. There's another point, E here. The E point, for most of cases, the E point, which is elastic limit, is slightly higher than the proportional limit. So as you can see here, okay, and within the E point, the spring can completely go back to its original shape after removing the load. Yeah, if you go beyond that, then you're going to end up with some plastic deformation. Okay, so that's the definition for for elastic limit. Okay, brilliant. I think that's all about this topic. Now, let's move on to something new. I want to talk about energy. Okay, energy. As you can see, I'm going to bombard you with quite a lot of new concepts. But before going through this slide, I want to show you something. I want to explain something. I want to have a little discussion about energy. Okay, let's have a look at this one. I got a spring. Just take the example of the spring again. We got load here that stretch this the spring and end up with a certain extension E here. And GCSE physics, we already learned that the work, let me change the color, let's use red color. The work equals force times displacement. Okay, in this case, force, of course, is just the load, and D is the extension. Okay, and D is the extension. Okay, and then so we know the work is related to energy change. Here, can you think of any energy that has been changed? Pretty obviously, we can see the height of the load is decreasing. That means the gravitational potential energy is decreasing. Okay, And because of the conservation of energy, there must be a certain energy. I don't know what that is. That energy gonna increase. There's gonna be an energy transferring from potential gravitational energy to a certain another form of energy. And that form of energy in this case is called elastic potential energy, because the energy has been stored in that spring is called elastic potential energy or string energy. Now let's just go back to my PowerPoint here. Okay, so now let's just go through this concept. So when the object has its shape changed by force acting on it, the object is said to be strained. Okay, I will go back to this maybe next lesson when we're talking about Young's modulus. Yeah, but so just try to understand what strain means. The work has to be done by the forces to cause the strain. The energy is stored in the body. So in the case we talk about, the body is a spring. So in the body as a potential energy, and when it's strained, and this potential energy has got name, that is elastic potential energy or string energy. Okay, now let's talk a little bit more about it. Load extension graph. Okay, so this graph is called a load extension graph. It's showing the relationship between load and the extension. This graph is pretty useful because we can quantitatively figure out the string energy. So I just give you the conclusion, and I will explain later. So the string energy is given by the area under the graph. So we can see in this case the graph is here, and the area under the graph in this case, of course, is a triangle, and the area is the string energy, because the triangle, so it's base times the height divided by 2, so it's half F times E. Okay, that's just the conclusion. I will explain it later. And if we know the spring constant K, the string energy can also be calculated using this equation. So the string energy equals half K E squared. Okay, try to remember these two equations. And now let's just explain why. Okay, and let's have a look at this example. We got a little item like a box, just it looks like a box. The box put on the surface, and I apply a force. Of course, because of the force, it will move a distance of d. And then, so the GCSE physics already said work equals F times d. Okay, and in this case, let's just say that F is constant. If F the force is constant, then we can plot a graph like this. Look, so when we apply F, and then so the distance starts, so the box start to move, and it would, after a certain time, it would make a displacement of d. So that's d. Okay. Of course, because the force is constant value, so that's why it's a straight line here, and that's F. And we can see, we know the work is F times d, and F times d, look, is just the area under that graph. So that's the work. Okay. Because it's a rectangle shape, the length and width timed together, we get the work. We get the area. So the area under the graph is showing the work. Okay. Now let's look at the case of the spring. If I have a spring here, and we got, because of the load, so it's been extended. Okay, and then we can plot the F, that in this case is the load, and the and the extension. The extension is just the displacement d here. Let's change the color to red. Okay, and then so the graph should be like this. That's based on Hooke's law. Because we know F in Hooke's law, F equals K times E. That's why, so it's a linear, is a line here. Okay, when F is 0 and E is 0, so that's the 0 point. And then we can look at the area down here. Of course, the area here is the work, and then to calculate it, we just figure out the area of that rectangular shape, and then so that's how we get this equation. So W, the string energy, equals half E times F. Okay, and also we know this, that's the Hooke's law, and put put it down here. And these two equations, we just rearrange it, and we'll be able to figure out that equation. Just a little bit of math. I think it's pretty easy to figure out that. So the so that's how these two equations come from. Okay, let's go back. Brilliant. So I explained these two equations. Now try to remember these two equations, and we'll look at the question. Okay, now I got a question for you guys to try. Let's just read for you. The spring has a spring constant 65 Newton per meter, and it's extended elastically by 1.2 centimeter. Calculate the string energy stored in the spring. Okay, just pause the video and try to answer the question. Okay, I'm just give you the answer here. Look, so we know from the body of the question, we can see K is 65 Newton per meter. And also we know the E, the extension, the elastic extension is 1.2 centimeter. And be careful, we need to be careful with the units. One is meter and the other is centimeter. So we just convert from centimeter to meter. Then we just simply use the second equation to do the calculation. If you substitute all the values, and you'll be able to get the final result, and that is 4.7 times 10 to minus 3 joule. So well done if you got it right. Okay, brilliant. Now let's just summarize what we have learned. We got some exit questions for you. Try to answer these three questions, and then to pause the video and answer these three questions. Okay. And finally, we got some homework for you to try at home. Okay, you pause the video. Okay, I think that's the end of the lesson. So have a good time. So see you later. Bye bye.